Hey there, this is Intro to Malloc ordering. Now, the ordering of Malloc and free is really, really important to understanding heap exploitation. But I think a lot of people will have a proportion with how. Oh my gosh, he put it on screen, heap feng shui. Only gods of binary exploitation know how to do that. We're going to take a deep breath. It's going to be okay. Heap feng shui is just the placement of heap chunks in a favorable way. And this is all about how the allocator gives out data, which means it's all about the ordering of Malloc and free. And that's what this section is about. I think a lot of people say, oh, I did some heap feng shui, and it sounds really cool. And it is cool, and it is difficult in these big systems, but it's all just the order of Malloc and free. It's not that bad. So this is my big overview of the ordering of Malloc and free. What I mean by this is Malloc will look at each one of these things in this order in order to take chunks. So first, it will look to the T cache for a particular size. In these situations, it will only look for exact size matches. So if I need a chunk of size hex 20, it will only pull chunks of hex 20 from the T cache, the fast bin, and the small bin. After that, it checks the unsorted bin. The unsorted bin is kind of weird, though. In the unsorted bin, it searches for an exact match. And if it can't find an exact match, then it will place the chunks into the small bin, large bin, and T cache bins, respectively. And what that means is that this is the only place that the small and large bins actually get chunks for, which is kind of weird. After that, it will look in the large bins for an exact size for what you need. After that, it will look for bins larger than exact fit. So maybe your allocation was hex 220 and there was a chunk of size hex 240 in the small bin, it will then pull that out. However, it only looks within the small and large bin for this situation. It doesn't look in the T cache or fast bin because those are considered fast entry bins. If it still can't find anything, then it will pull data from the top chunk itself. So it will take the top chunk, it will shrink it, and it will give you that particular piece of memory. If it still can't do that, then we'll try to extend the heap with a call to SBRK. And at this point, it's going to lengthen the heap. If it still can't find anything after that for whatever reason it can't extend, then it will use mmap chunks. And mmap chunks are chunks above a certain size threshold most of the time, though. And if it still can't find anything, then it returns null. And although this doesn't seem that interesting, one of the iOS jailbreaks actually was because of this. The developer of the boot ROM had expected null to be returned, but in fact 8 was returned. Well, 8 isn't null, so 8 must be a valid address, and so it used that. And that was actually the one of the big jailbreaks back, 5 years ago or something. It's a pretty cool bug, though. So, as I said, the unsorted bin section is the only time chunks actually get put in the small and large bin. Free doesn't do that, which is kind of weird. So, with free, it's a little bit simpler, and I think it's good to chat about. So first, there's kind of two edge cases. First, if it's a null pointer, then it will just return. Second, if it's mmapped, then the chunk will be munmapped, meaning that it will remove the memory mapping directly for you. This is what the M bit on the chunk size metadata is used for. The next two it checks are the Tcache and fastbin. If it is in the Tcache size and the Tcache for that size isn't full, then it will put it in there. After that, it looks in the fast bins if the chunk will fit in the fast bins. And this is particularly important for understanding how the free process works. After that, we try to put it in the unsorted bin. And when it goes into the unsorted bin, it will try to consolidate neighboring free chunks from the small, large, and unsorted bin. And at that point, it will actually add it to the unsorted bin. For step 6, if the chunk is adjacent to the top chunk, then we'll consolidate with the top chunk. The reason I put this for 6 is it's kind of part of 5 because it's part of the consolidation process, but it feels like its own special case. So again, we have a free chunk right next to the top chunk, so it just extends the size of the top chunk. Now, the other one is if a free chunk has a size larger than 2 to the 16th power, then it will also remove everything from the fast bins and throw them into the unsorted bin. And the reason it does that is because we can have fragmentation problems. Imagine if we had 20, 20, 20, 20, but we needed a size of hex 1000. Those size 20s aren't going to be very helpful, so sometimes it will combine the chunks in the fast bins. This is a crazy diagram I found online of the ordering of Malloc and free. It is accurate. It doesn't include the T cache, but it is fairly accurate. But this is my high level understanding of how it works. There are things like the last remainder chunk and other things. So I recommend reading the Malloc source code. I know that sounds absolutely terrifying, but once you understand the data structures and stuff at a high level, it becomes much easier to read. The other thing that's good to throw in here is the sizing of Malloc. Malloc will always need 8 extra bytes for the metadata, and it always will use groups of hex 10 on 64-bit. The smallest chunk we possibly can have is hex 20 because it needs room for the prev size, FD, and BK at all times. The large chunks are weird, but because the large bin chunks are much bigger than hex 30 bytes, it doesn't really matter. As an example, an allocation of hex 20 will create an allocation of hex 30. Hex 38 will return hex 40. An allocation of 0 returns the chunk size of hex 20. I know, annoying. So, I know you're probably a little sleepy right now. This isn't the most entertaining thing in the world. It's data structures and stuff all over again from the computer science class days. But I hope you see the deep and profound understanding of this. Now, let's think about some techniques that could fall out. What if I corrupt the size information? Well, if I corrupt the size, I could make a chunk think it's bigger than it really is, and I could produce more powerful buffer overflows. Or what if I corrupted the FD of the linked list and changed the location of that? Or now that I know that the FD and BK are literally just libc and heap pointers, I could get good information links. Now, all of this information is super helpful for getting deeper and deeper into this. I gotta say, one does not simply break heaps. You must learn how the heap works first. So as a recap here, we have chunks which have a prev size, a size which has metadata points like the prev and use bit, FD and BK pointers. Then there are bins, and bins are just pointers to the beginning of a linked list. And there are unsorted, small, large, fast bin, and T-cache bins. The ordering of unsorted is FIFO, and I think that's also the case with the small bin. And then the fast bin and T-cache are last in, first out. And we also learned about the ordering of Malloc. And this is the cheat sheet you guys can use. It's all pretty. I can't do anything that cool. I drew this on a piece of paper and told some marketing person to make it look nice. And they did a good job. So you've completed the most important section of the course. There is also an exercise on the ordering of Malloc stuff that you should go through as well. But, thanks for your time. Good job.